Valentine losers, and we have taken part in the off-road terrain semantic segmentation, which is presented by Duality Hackathon. So, the problem statement is that we are given a data set of off-road autonomous navigation vehicle, and we have to train on the synthetic desert imaginary and evaluate on the novel desert environment. Then moving to the data set, we are given with the training, validation, and test data set. And there are 10 classes, which are trees, lush bushes, dry grass, dry bushes, and all. So this is the class distribution with the sky at the max of 38% and of 1.2 billion count, and the flowers, dry bushes, and logs are at the bottom with very low. So after analyzing the test, we have got to note that the absent classes like lush bush, ground clutter, flowers, and rocks receive 0 IUA and lowering with the reported overall MIU by about 40% relative. So starting, I have taken so many approaches. So starting with our phase one approach, which is the baseline, in which we have used the VITS 14, which is for 22 million parameter model, and we have used weighted cross entropy with inverse square root class weight. And for the augmentation, we have used horizontal flip, brightness and contrast, Gaussian blur, and elastic transform grid distortion, giving us the validation MIU 40.38 and test MIU of 25.17. And then in the phase 2, we have used the augmentation tuning. We have done augmentation tuning. We have added the color jitter, random rotation, cross dropout, and which due to which our probability increased to 0.7. And validation MIU, we got about 2.12% extra, and in the test we have got a little less of 0.37 minus. And then we have implemented the phase 3, in which we have used a larger backbone model, Dino V2 VITB 14, which is based on a 86 million parameter. On that we get a validation MIU of 58.8 and of test MIU of 23.5. Then in the phase 4, we implemented multi-scale fusion, and we have combining features from multiple transformer layer, which can improve our generalization. This is our hypothesis. So we have extracted features from layer 25811, configuration 307, dim feature vector, and due to this we have received validation MIO 57.85 and test MIO of 22.18. Then we have implemented the phase 5, on which we have implemented the permeable layer weights, and our hypothesis is that if we let the model learn how to weight each layer contribution, so we get the highest validation MIU on this of 60% and got 22.3 on test MIU, which is our lowest on all the phases. And this difference confirms severe overfitting of the model. And in the phase 6, we have implemented the pseudo level self training, and we have run the phase 5 model on test images and keep pixel with soft max confidence of zero point 0.9 as pseudo levels, and due to that we get validation MIU of 57.58. And we get to know that only 28% of the test pixel met confidence threshold, mostly sky landscape. And this is our generalization paradox. This is the validation MIU and gap. We got best on the phase 5, and on the test MIU we get best on the phase 1. Then we have started our root cause analysis. There in phase 5 we get the overfitting of the model, then domain shift magnitude. Then the test set differs systematically as the lightning, camera angle, terrain composition, variation are different from the dataset on which we have trained the model. And this is our phase 1 and phase 5 per class MIU. And then we have implemented the assemble strategy. We have taken selected the 8 checkpoints with a validation MIU of 58% from all the faces. Then run the our ensemble model and compared several fusion methods also. Like we have implemented the entropy weighted voting, and this is our visualization. Validation performance closes our training phases. Validation loss across training phases, and this is our final performance comparing across all the phases. So this is our per class performance on test set, and we get 0 on loose push, ground clutter, flowers, and log as they are not present in the test data set. In the detailed failure model, only 38% of the rock pixel misclassified as landscape, 28% 0.4 as dry grass. And what could be the root cause? That test has 80% rocks, and in training we have only have 2% rocks. So in trees, similar in the trees, 30.4 misclassified as tri bushes. The training trees greener, test trees browner. This is the cause of our root. That's why you get a lower IU. In the dry bushes, similarly, there's very rarity of 1.1% of training pixels. That's why then then we reach to the challenges and mitigations. So we got three challenges, and the first one is severe domain shift. We have attempted stronger augmentation, multi-scale features, pseudo labeling, and assemble of diverse model with improvability would recovered 1.14% of gap only. Then the challenge two, there is extreme class imbalance. uh, Classes like rocks and flowers are less than 3%, which influence our training a lot. Then we reach to the challenge three, which is small object detection, as the problem that rocks and locks are missed entirely as there are less than 50 pixels. In the future we can use hybrid CNN transformer architecture or dense prediction transformers which could better handle small objects. Then in chess, at the last and the most important challenge we got and faced is the missing test classes. Four classes is absent from the test class fully, which lowered our MIU by 40% relative. And till now we have learned these lessons for off-road segmentations. Validation performance is misleading as we got 50% validation and very low MIUU on test. Simple artificial generalize better, like we use the phase one. Domain shift is real challenge. Assemble diversity beats individual performance. For hackathon strategy, start simple and validate on test. We have we have start evaluation very late. Phase one, if we have tested the phase one earlier, we might get better MIU or use some other approaches. So what we could do in the future is like we can implement more improvements. We can implement coral adversarial alignment and test time adaptation. We could use better loss functions or we can do the architecture tweaks by like we can use hybrid CNN transformer or hierarchical transformers. For the long term we can use the better regularization models like VIT large, which is a 304 million parameter model. We can use multi-model fusions, self-supervised learning. So this is our summary and the final remarks that this project demonstrate both power and the pitfall of foundation model fine-tuning for domain specific tasks. The systematic progression through our all the six phases revealed that simple and less adapted model often generalize better. So at the last, so we have integrated our requestly API client into our development workflow to test and debug our model serving API. We have built a fast API application that loads our phase one model, exposes endpoint for inference like slash predict returns PNG marks slash predict dot JSON returns class distribution. Using requestly, we can organize all the API endpoints into a collection. Wrote post a response script to attempt automatically evaluate the output format and log inference times. Switch switch between environments with one click, ensuring consistent testing. Leverage requestly history to replay and debug failed requests, which help identify input size mismatch. So at last, this is our project, and the code, the checkpoints, and final prediction are available in our GitHub repository and the drive links which we have attached. Thank you.